Okay, let's go over the answers to the mid-year review. Let's get started. Okay, the first question is a transversals question. It says, identify a pair of same-side interior angles. So 1 and 7, let's see, 1 and 7, that's here and here. Those are corresponding angles, not same side or consecutive interior angles. There's another way to say same side interior angles. But 1 and 7 are corresponding angles. Those are congruent, but they're not what we're looking for. 3 and 8 form a linear pair. They're supplementary, but they're not same side interior angles. In order to be same side interior, they have to be on the same side of the transversal, that side, or all on this side, and between the parallel lines. So between this line and this line. So we're looking for 8 and 7 or 3 and 4. 2 and 5, now 2 and 5 are same side exterior angles. They're outside the parallel lines, but 8 and 7 will work. Just have to change my color. Okay, there we go. 8 and 7. Let's look at number 2. What are there 3 pairs of corresponding angles? So 1 and 2. Nope, 1 and 2 are a linear pair, not corresponding. How about 1 and 7? 1 and 7 correspond. 8 and 6? 8 and 6 correspond. 3 and 5? 3 and 5 correspond. Okay, that works. I'm just going to double check the other ones. 1 and 2, I know those are a linear pair. And 1 and 8, those don't correspond. 1 and 8 are a linear pair as well. So the answer to this was B. Okay, let's move up to number 3. Find the value of X. L is parallel to M. I'll put an extra couple of arrows in here so we can see that they're parallel. The diagram is not to scale, that's fine. We weren't going to use a protractor anyways. Okay, so 5x is here. 5x is here, and then 130 is there. And those are corresponding angles. So if the lines are parallel, corresponding angles should be congruent. So 130 equals 5x. And divide both sides by 5. And 5 goes into 130 26 times. So x equals 26. Okay, moving on. In the figure, angle 6 and angle 3 are, okay, 6 is here. 3 is here. They are consecutive interior, or you could say same side interior. Consecutive because they come one right after the other, and interior because on the same, consecutive also meaning on the same side of the transversal, and interior meaning between the two parallel lines, or they actually don't have to be parallel, but between the two lines that the transversal cuts through. So those are consecutive interior angles. Also, consecutive interior angles, if the lines are parallel, are supplementary, not congruent. So the fact that 3 is obtuse and 6 is acute should give that away. Page 2. Already on page 2. Question number 5. In the figure, L is parallel to M. L is parallel to N, and R is a transversal. Which of the following is not necessarily true? Is 8 congruent to 2? Yeah, 8 and 2. 8 and 2, those are alternate exterior angles. 2 and 6. 2 and 6, those are corresponding angles. Both alternate exterior and corresponding angles are congruent. 5 and 3. 5 and 3, they're both obtuse. And they're alternate interior angles. Those are congruent. And 7 and 4. 7 is here. 4 is here. Those two actually don't have a special name for their relationship, but they are not congruent to each other. They could be congruent if all of them were right angles, but they're not necessarily congruent, which is what the question asked. All right, moving on to number 6. Find the value of x that will allow you to prove that CD below is parallel to EF. Okay, we need the value of x, and then there's no x. Oh, wait. If the measure of angle 1 is 3x plus 30, and the measure of angle 2 is 81. Now, angle 2 and this angle right here are congruent to each other if the lines are parallel. Those would be corresponding angles, and they are congruent to each other, which means that this angle 1 and that other angle that I mentioned there are a linear pair. They are supplementary. So that means that I'll call this angle 3. If 2 and 3 are congruent and 1 and 3 are supplementary, that means 1 and 2 are supplementary. That's a transitive property. So I know that 3x plus 30 plus 81 equals 180. Excellent. We have some like terms that we can combine together. 30 and 81 add together to be 111. So 3x plus 111 equals 180. And if I subtract 111 from both sides, I get 3x equals 69. And if I divide both sides by 3, I get x equals 23. So that's the value of x. All right, number 7. This one actually looks a little bit more confusing than it needs to. Imagine that this is a transversal. It goes all the way through. And we can even imagine that this line over here just doesn't exist. We'd have a normal transversal problem, and 2x and 7x plus 27 would be consecutive interior angles. So I know consecutive interior angles are supplementary if the two lines are parallel. So 2x plus 7x plus 27 equals 180. Those two will also be supplementary. It's also kind of a giveaway when one's acute and one's obtuse. I know they're not going to be congruent. They must be supplementary. So 7x plus 2x is 9x. Okay, that's as much simplification as I can do. I can subtract 180 minus 27 and get 153. And 153 divided by 9 is 17. X equals 17. Okay. Now we have these two angles. Oh, they are alternate interior angles, which are congruent to each other. So 2x minus 26 equals 108. The giveaway, those are both very obtuse, 108 degrees. So if I just solve this equation, I will add 26 to both sides. 108 plus 26 is 134. So 2x equals 134. And x will equal 67. Very good. All right, let's move on. Okay, let's continue with number 9. Let's classify triangle PQR. And judging by the answers, we're classifying it by the length of its sides. So scalene meaning all the sides have different lengths. Isosceles means 2 or more sides are congruent. And equilateral means all the sides are congruent. So we have 2 sides that are congruent. That one's 8 and this one's 8. Those are congruent. 10's not congruent to 8. It's its own thing. So it's not scalene because we have 2 congruent sides. It's isosceles. It's not equilateral because we only have 2, not 3. Okay, number 10. If triangle ABC is congruent to triangle XYZ, which of the following can you not conclude as being true? Okay, so we have a congruent statement here, which means all the pieces of the congruent statement are congruent to each other. So we can say 6 different things about a triangle congruent statement. I can say angle A is congruent to angle X because they are both listed first. This was first in this one. This was first in this one. Likewise, B and Y will be congruent. Angle B is congruent to angle Y. And angle C is congruent to angle Z. So I can get all of that about the angles just from looking at the congruence statement. But also I can say that sides AB, the side AB is congruent to XY because they occupy the same relative position in each part of the congruence statement. AB are the first two letters, XY are the first two. That means that segment AB has to be congruent to segment XY. Likewise, BC would be congruent to YZ. And AC, either the first and third, is congruent to XZ. Oh, I forgot a segment marking on top of the YZ. Okay, so one of these is not true. So first off, we have AB is congruent to XZ. Well, right over here, I mean, right off the bat, AB is congruent to XY, not XZ. AC is congruent to XZ. So I think that this is the one that will not be congruent, but always double check the other ones to make sure. BC is congruent to YZ. Yep, I agree. BC is congruent to YZ. Angle A is congruent to angle X. I agree. Angle A is congruent to angle X. And angle B is congruent to angle Y. I agree. Angle B is congruent to angle Y. B, C, and D all check out. So answer A is the one that is not true. Question number 11. If BCDE, so it's a quadrilateral, BCDE is congruent to OPQR, then DE is congruent to, so they want you to break this apart. DE is the third and fourth letter in BCDE, the name of that quadrilateral. Because they're congruent, I know that DE will be congruent to segment QR because they have the same relative position. They're the third and fourth letter in the congruent statement. So DE is congruent to QR. That's D. All right, let's look at number 12. Based on the given information, what can you conclude and why? P is congruent to T. Angle P is congruent to angle T. I can mark that. PR is congruent to RT. I'm just going to put one line through that because it's the shortest segment. Okay, that's the information they gave us. Remember, there's generally three things you need to know in order to prove triangles are congruent to each other. It's either three combinations of angles and sides, or in the case of hypotenuse leg, you need to know that they're right triangles and two sides. In this one, we don't know that they're right triangles, but I do know that there is a vertical angle around point R. There's this and this, and those two are going to be congruent to each other. And we have two angles in the side inside of those. So I'm looking at angle, side, angle. So it's definitely not this one and this one. Those say side, angle, side. So out of this, PQR is also what's listed. PQR is congruent to RTS or TSR. Well, P, the first one, that is congruent to T. So I have to make sure that the P here matches up with the T. And the other one, it matches up with R, which P and R are not congruent to each other. P and T are. So the correct answer is B. We do have our angle, side, angle, side, angle, matching up with angle, side, angle. And not only that, our congruent statement is in the proper order. P, Q, R matches up with T, S, R. Number 13, from the information in the diagram, can you prove that triangle FDG is congruent to triangle FDE? FDG, FDE, they kind of look congruent to each other, and we know a lot about angles. We have pairs of angles that are congruent. This angle is congruent to this one is congruent to this one is congruent to that one. That's all the possible angles. But angles aren't enough. You need to have at least one side, and there's no marking on this diagram that says that one of the sides are congruent. However, there is a side that is the same in both of the triangles. DF, that side length is the same length in both triangles. It's a reflexive side. So you do know at least one side. You know that one. Now, I could easily prove this using either angle side angle or angle angle side, but out of my options, angle angle side is not one of them. So I will have to use the angle side angle one. AAA is not a congruence postulate. That's not it. There's a similarity postulate called AA, but AAA is not a congruence postulate. SAS would be nice, I guess, but we only know one side in each triangle, so we can't possibly use two sides of SAS. And no, I can prove these congruent. So the answer was A. No, 14 is actually over here. Hello. What must be true in order for triangle ABC to be congruent to triangle EDC by the side angle side congruence postulate? Okay, and then they give us this diagram. It's a little rough. Let's try to fix it a little bit. That's supposed to be a B. And we have a little line here and a line here. So that's good. That helps us with that side. Okay, so let's see. I also notice this is one of the bow tie problems, meaning it kind of looks like a bow tie, which means that you have a vertical angle in there. It's not marked ahead of time. Sometimes it could be, but in this case it wasn't. But I know that's a vertical angle, and I know because of the vertical angle theorem, all vertical angles are congruent. So those two are congruent to each other. So if I wanted to use side angle side, I would need, first of all, I would need another side in each of the triangles, and it would have to be on the other side of the congruent angle. So the only possibility is if I use AC is congruent to EC or CE. And that answer is C. Then I could use side angle side. Knowing those other angles wouldn't help me in answer A or answer B. And answer D would be like a side angle, which isn't a postulate. Like the angle has to be directly in between the two congruent sides to use side angle side. So that's why I picked C. AC is congruent to segment CE. Ooh, 15. Another bow tie problem. Here we go. Okay, refer to the figure shown. Which of the following statements is true? So TV is congruent to WV, or segment TV is congruent to segment WV. Also, UV, segment UV, I'll use 3 for that one, is congruent to segment XV. Perfect. That's great. And once again, I identified this as a bow tie problem, which is just two triangles that have a vertical angle that is congruent between the two of them. So that would be like both sides of point V, or if you wanted to say it correctly, something like UVT is congruent to XVW. Okay, so I can solve these. I can prove these two triangles are congruent using side angle side. You have two sides in the angle between them, congruent between the two shapes. So we're not going to use that one, and we're not going to use C. So our question is, which one of these two has a correct congruent statement? So they said TUV. Both of them start with TUV. So from T, let me do it in a different color here. So from T to U, and then to V. Well, I want to make the same thing happen on my other one. So angle T corresponds with angle W right here. Angle U, the one that kind of sticks out there, matches up with angle X. And then angle V matches up with angle V. So there you go. So WXV, triangle WXV is what I'm looking for. And that is true only here. Oh, let me switch back. Number 16, tell which methods you can use to prove that triangles are congruent. If no method can be used, write none. Okay, we have right triangles. That's good. That brings HL as a possibility. In order for that to work, though, we would need the hypotenuses to be the same, which in this case, they actually are. This is the hypotenuse, and this is the hypotenuse, and they are congruent to each other, We also need one of the other sides, one of the legs, to be congruent. That leg is congruent to that. And of course, you need that they are right angles, and they are. So actually, we have everything we need here to say these two triangles are congruent using HL, or hypotenuse leg theorem. Moving on to 17. Oh, isosceles triangle. Two sides are the same. That means we have base angles that are the same. So this is 66 degrees. This over here also has to be 66 degrees. So what is the value of x? So what is that angle up at the top? Well, I know that 66 plus 66 is 132. And I know all three angles added up will add up to 180. So if I subtract 132 from 180, I will figure out what angle x is. And that's 8, and that's 4. Angle x will be 48 degrees. Or the measure of angle x will be 48 degrees, I should say. Okay, so that's 17. Now let's look over to 18. What is the value of x? Okay, well, it's a isosceles triangle. They give us the vertex angle F, which is obtuse. It's 95. And so angle D and angle E will be congruent to each other. So let's see what we're working with after we subtract out the 95 degrees. So 180 minus 95 equals 85. Now I have 85 degrees to share between angle D and angle E, so both of them will be congruent to each other as well. So 85 divided by 2 will get me what each of the angles are, and 85 divided by 2 is 42.5. So our answer is D. Okay, next we're into some proportions, which means we're probably getting close to similarity. Now, we have a proportion here, 5 over A equals 25 over 35. And if you wanted to, you could go right into it and start cross-multiplying, and everything would be great. What I like to do is simplify anything that's possible. So we have a fraction on the right-hand side, 25 over 35. And I feel like I can reduce that because they both end in 5. So if I divide the numerator and denominator by 5, I would get 5 over 7. Now, if 5 over A equals 5 over 7, wouldn't A have to be 7? And if you're really unsure about that, you're like, well, yeah, that looks like it's right, but I'm not too sure. You could always cross-multiply at this step. You could take the A and multiply it by 5, 8 times 5, and set that equal to 5 times 7. And 5A would equal 35. And divide both sides by 5. And once again, you would arrive at A equals 7. So that's 2 of the ways to find this. There's actually more, but 2's enough for now. Let's move on to 20. 3y minus 8 over 12 equals y over 5. Okay, you have 2 terms in the numerator that are being subtracted. You can put parentheses around those. Now, those are like inferred parentheses, but if our next step is to cross multiply, that will come in real handy. So 5 times that should equal 12 times y. And remember, we have a number outside a set of parentheses now. This is why the parentheses are important, because you need to distribute that 5 to each of the terms. So 5 times 3y is 15y. And 5 times 8 is 40. So we have 15y equals minus 40 equals 12y. If I subtract 15y from both sides will end up being negative, and that's fine. But negative 40 will equal negative 3y. And if we divide both sides by negative 3, we'll end up with y equals 13 and a third. Which, if we kept it as an improper fraction, would be 40 over 3. Moving on, 21. All right, the two rectangles are similar. Which is the correct proportion for corresponding sides? Now, there are a lot of different ways you can set up this proportion, but only one of them is going to yield you the actual answer. But any of the correct proportions can be manipulated to look like whatever one is the correct answer. So this is how I always do it. I choose one of the shapes, and I will choose the smaller one on the left first because I read left to right, and I will choose the larger one second. And I will list off the sides on the first one that I am aware of. So the smallest side is 4, and the larger side is 12. I always go small side first, then the larger side. Now, I'm not going to put the units here because the units are kind of irrelevant at this point. We know we're just making a proportion of the sides, so as long as the units are the same between the two shapes, we don't have to write the m after. Now I'll move on to the second shape, and I will list off the smallest side under the left, 8, and the larger side under the right, 24. Now, fight the urge to reduce these because none of the answers are reduced, so we have to keep it just like that. It's not just, don't just make it 1/2. Okay, now, hopefully when I look, I see the proportion that I made as one of the possible answers, and it's not A. That A doesn't look like mine. It's not B. It's not C. It's not D. It's not going to work. Okay, so now we have to manipulate this a little bit, and we're going to do that by swapping diagonally. Or the other thing you could do is just take the reciprocal of both sides and rewrite that. But I don't think that's going to work out. We'll have to swap some sides here. So 4 over 12, is that any of them? We have a 4 over 12 there and 4 over 12 there. One of those is probably going to be the answer. Let's see. Now, notice these two are the same as each other. They're just reciprocals of each other. So they both should be, if they were right, both of them would be right. But what I'm really looking at here is if I exchange the 4 and the 24, you could just like exchange those freely because it's one of the properties of proportions. But also think about it, if we were going to cross multiply, it doesn't matter if you do 24 times 4 or 4 times 24, it would give us the same answer. And so that's what I always think of. So if I rewrote this, and I'll write it in a different color, if I rewrote this as 24 over 8 equals 12 over 4 by swapping the 4 and the 24, I think one of those will come up, and it's B. Look, B is the symmetric property of that. It's 12 over 4 equals 24 over 8, which is just as correct. And that's how you have to do it. So sometimes you have to work with the proportion you made, and even if you made a correct proportion, it won't show up. You'll have to manipulate it slightly. But that definitely works. 12 does compare to 4 the same way that 24 compares to 8. So that works for me. Let's move on. Okay, number 22. Are the polygons similar? If they are, write a similarity statement and give the scale factor. Okay, we have 3 sides and an angle. The angle is congruent and they look like they have the same orientation. So I'm immediately thinking maybe the side angle side similarity postulate will work for this one. Now, in order to use that postulate, I have to make a proportion out of the sides. So once again, I will pick, this is my first shape, this is my second shape. And in my first shape, I'll list out the sides from smallest to greatest, 12 and 18. And the second shape, I will do the same. Smallest side is 10, larger side is 15. And I will see if these reduce to the same scale factor. So 12 over 10 is 6 over 5. And 18 over 15, if I divide both of those by 3, I will get 6 over 5 as well. That's great. That's my scale factor, 6 over 5. Now, that's one of my scale factors. It could also be 5 over 6, but having the angles be the same and having the scale factor be the same. I know that these are similar, so D is not an option. Okay, now when they wrote theirs, they wrote RST first. So even though I wrote mine the other way, I wrote, WVU first equals RST. We can just swap that and put the RST on top and the WVU on the bottom. That would be 5/6. So because they wrote it backwards, that one's out. Okay, and we have RST is similar to, let's see, angle R should be similar to angle U. And the only one where that is true, I mean, they're both 32 degrees, so those should be the ones that you immediately start with. And the only answer that has that part in it is B. So I choose B. Now, same directions. Let's look at down here. Okay, we have some parallelograms, it looks like. Being that all the sides are the same, I probably could prove that these are parallelograms. I am going to assume that all the angles are the same, or the corresponding angles are the same because they are parallelograms. And that's one of the properties of them. I'm going to skip right to the making sure the sides are proportional. So shape 1, the small side is 4, the larger side is 12. Shape 2, the smaller side is 1.7 and the larger side is 3.74. Certainly a good time to bust out a calculator here. So 4 divided by 1.7 is approximately 2.353. Okay, so if 12 divided by 3.74 is the same, then they're similar. So 12 divided by 3.74 is approximately 3.209. Those are not the same numbers. These are not proportional. So the polygons are not similar. They do not have a standard scale factor that goes through the problems. Now, if I got one and then the scale factor was like upside down from what they wanted it to be, that's fine. I can just take the reciprocal of it and that's totally fine. It's still a correct scale factor. But these are two completely different numbers, so that just doesn't work for me. Given that triangle ABC is similar to triangle DEF, solve for X and Y. Okay, ABC, DEF, solve for X and Y. You got it. By giving us the similarity statement, we can make a proportionality statement out of that. I will say AB, BC, and AC. And I just got that from reading this. AB, BC, and then AC is similar to DE, EF, and DF. I always follow the same procedure when I do that, so I know that everything will match up perfectly. So AB over DE equals BC over EF equals AC over DF. That's called a proportionality statement. And what I need to do now is substitute in the values from the diagram into that proportionality statement. So AB is right here, and that is a Y. Just put the Y right into the fraction. DE is right on the other side, that is 6. Then we have BC, which is 5, and EF, which is 4. And finally, we have AC, which is 9, and DF, which is X. So Y over 6 equals 5 over 4 equals 9 over X. Great. We can't solve this all at one time, so I will just worry about this side first, just the first part of it. So Y over 6 equals 5 over 4. And I could cross multiply this. 4Y equals, and then 6 times 5 is 30. So Y equals 30 divided by 4, which is 7.5. Okay, so right off the bat, I'm going to cross out B and C. Now let's try the other one. Switch colors again. All right, 5 over 4 equals 9 over X. So 5X equals 9 times 4, which is 36. And 36 divided by 5 is 7.2. So our answer is A. So moving on to 25, and they did not give us a lot of room for this, but, and for some reason there's D's in there. Don't ignore the D's, those are triangles. Triangle ABC is similar to triangle DEF. Okay, so I can make a proportionality statement here. I'll do it quickly. AB, same method as last problem. BC and AC over DE, EF, and DF. And those all equal each other because we know they're similar figures. And so now I can substitute AB is Y, DE is 9, BC is 10, EF is 6, and that equals AC, which is 18 over DF, which is X. So once again, I have to do this one side at a time. Y over 9 equals 10 over 6. And I could reduce 10 over 6. I don't have to. I'm just going to multiply 10 by 9, 10 times 9, and then divide that by 6. So 10 times 9 is 90. 90 divided by 6 is 15. Y equals 15. And we'll break it apart to the other side. 10 over 6. I'll reduce it now. 5 over 3 equals 18 over X. Okay, 18 times 3 divided by 5 is 10.8. So X equals 10.8. And that's what Y and X are. That wasn't too bad. All right, let's move on to 26. Ooh, which side lengths allow you to construct a triangle? So remember, the two smaller sides have to add up to a number larger than the largest side. Otherwise, the triangle doesn't connect to each other. So if you have sides 2, 3, and 8, the two smaller sides, 2 plus 3, must be greater than 8. And 2 plus 3 is 5. So 5 is not greater than 8. Okay. In B, they try to mess you up by putting them in a different order. The smallest side is 1. The middle length side is 4. And then the largest side is 9. So 1 plus 4 has to be greater than 9. 1 plus 4 is 5. Is 5 greater than 9? I don't think so. Okay, the next one, 7, 2, and 2. So your smallest sides are both 2. 2 plus 2 is 4. Is that greater than 7? Nope. Okay, hopefully the last one works. Otherwise, this is a broken problem. Your smallest side is 6. Your middle length side is 8. Is that greater than 10? Yeah, 6 plus 8 is 14. 14 is greater than 10. That one checks off. Our answer is D. All right, hopefully there's some more of these. Oh my goodness, there are. Two sides of a triangle have the length 7 and 13. The third side has a length that is... Okay, so 7 might be the smallest side, or it might be the middle side. And 13 might be the middle length side, or it might be the longest side. So we have to solve this both ways. So first, I'm going to assume that 7 and 13 are the smallest sides. So 7 plus 13 equals 20. So I know that my third side has to be smaller than 20. And now I'll pretend that 7 is the smallest side, 13 is the middle length side. No, let's pretend that 7 is the middle length side, 13 is the longest side. So 13 minus 7 equals 6. So I know that if that's the case, my smaller side has to be greater than 6. So X has to be greater than 6 and less than 20. Less than 20 and greater than 6, that's B. Yeah. All right, two sides of a triangle have sides 4 and 13. The length of the third side must be greater than something and less than something else. All right, same problem. 4 and 13, we have 4 plus 13, which is 17. So it has to be less than 17. And it has to be greater than 13 minus 4, which is 9. So our third side has to be greater than 9 or less than 17. Anything in that range works out. So our answer to that is D. We could have stopped after the 17. All right, let's scroll-a-rooney. Down we go. Which of these lengths could be the sides of a triangle? Oh, here we are again. Same type of problem. 22, 5, 15, and 6. So take the smaller two sides and add them together. So 6 plus 15 is 21. 21 is less than 22. This is impossible. The two smaller sides added together have to be greater than the longest side. So the next one, 8 and 12. 8 plus 12 equals 20. That's equal. It has to be greater than, not equal. So that doesn't work. Okay, 5 and 15. 5 plus 15 equals 20. That's smaller than 22. That's not okay either. Okay, hopefully this one works. 8 plus 13 equals 21. Is 21 greater than 20? It is. Huzzah! Now we get into the real fun ones. Here we are. Exponents, roots, and polynomials, the third section of this. Okay, so we have a bunch of q's being multiplied by each other. Q to the 7th times q to the 5th times q to the 4th. Well, remember, this is like 7 q's being multiplied times another 5 q's times another 4. You actually end up adding those exponents. So 7 plus 5 is 12. 12 plus 4 is 16. We end up with q to the 16th, which is C. Now, why isn't it 3q to the 16th? Well, because there are no coefficients other than 1 for each of these terms. So if we were to put 1s there, you'd multiply those 1s in front. 1 times 1 times 1 is 1. That's why it's q to the 16th, not 3q to the 16th. Oh. What about these? Okay, so we have one coefficient. It's negative 3. That will be multiplied by nothing else because there's no other things. There are no other coefficients other than 1. Okay, we have w and w to the 7th. That's 8 w's total being multiplied. I'll just write that as w to the 8th. Then we have c to the 3rd power and c to the 5th power. So there's 3 c's times another 5 c's, which is c to the 8th. Our answer for this will be A. Very similar problem next. Oh, this one has 2 coefficients though, negative 3 and 2. And we're multiplying. That's the invisible symbol in between. Negative 3 times 2 is negative 6. And then C's, we have a couple of those. 8 and 6. So that's 14 C's total. C to the 14th. And finally, we have 8 D's here. None will be added to that. It will just be remained as D to the 8th, which once again is A as our answer. Nope. Let's go up over here. Oh. Power of a power. This is fun. C squared to the 6th. Remember, if you wrote this out, it would be like C squared times 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 C squared. 3, 4, 5, 6. That would be what that is. And adding all those up together would be C to the 12th. But a faster way to do it is just to multiply these exponents. Raising a power to a power, you multiply the exponents. 2 times 6 is 12. Either way, our answer is D. (35) 5t to the 3rd, r to the 8th. Everything is going to be raised to the 2nd power, or squared. The 5 will be squared, that's 25. T to the 3rd will be squared, which means multiply. 2 times 3 is 6. T to the 6th. And r to the 8th will be squared, so that's r to the 16th. So 25 t to the 6th, r to the 16th. Same thing here. Everything gets raised to the 3rd power. Now you can think of the -4 in this case as being a -1 and a 4, or you can just think about it as a -4. Your answer should be the same either way. -4 to the third power. 4 to the third power is 64. So -4 times -4 is positive 16, and positive 16 times -4 is negative 64. Because it's an odd exponent, the negative sign will carry through to the answer. If that was an even exponent, the negative sign would drop out. All right, t to the 8th, 8 to the third power is t to the 24th. And r to the 6th, 6 times 3 is 18. R to the 18th. So raising a power to a power, it distributes to everything, and it is just magical. It gets multiplied. Oh, here we go. All right, 36. A squared times a to the -9th. No, there's negative exponents here. I was told there would be no exponents that are negative. That's okay. We're all set. I deal with the negative part first, and what it means is put it in the other part of the fraction. You're like, what fraction? There's no fraction there. Well, if there's no fraction, that means put it in the denominator of a fraction you just made up. But the only thing that has a negative exponent is the a to the -9th. The a squared does not have a negative exponent. It will stay on top. So this will be a squared over a to the 9th. And now we can use our quotient property to, you have 2 a's on top and 9 a's on the bottom. So that's like a times a over a times 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 a. I think 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, they started to look like 9s at the end there. Okay, I like to think about these as canceling the factors out rather than subtracting the exponents. So that will cancel that out. That will cancel that out. But we still have 7 a's left over on the bottom here. So I will just rewrite it as 1 over a to the 7th. And that is my final answer. (37) Rewrite the expression using positive exponents. Okay, we have negative exponents, but be very careful about what parts have negative exponents. This y has a negative exponent. Also, this x has a negative exponent. But that 9 does not have a negative exponent. So this, rewritten with positive exponents, we have to take these negative exponents and move them to the numerator because they're in the denominator. So this will end up being 3x to the 3rd, that was already there, times x squared times y to the 1st, all over 9. And I guess that's correct. We rewrote the expression using positive exponents. However, that is not in simplest form. And most of the time, even though they don't say it, math tests want it to be in simplest form. So I can reduce the 3 over the 9. Check this out. That becomes a 1. That becomes a 3. And so I have no more coefficient in the numerator. But I have an x to the 3rd times x squared, which is x to the 5th. Y to the 1st, I can just leave it as y over 3. And that's as simple as I can make that. Each exponent only appears once. Everything else has been like combined together. No more coefficients can be simplified. There we are. Simple as can be. Okay, question number 38. Rewrite the expression using positive exponents. Not only that, we have some 0 exponents in here. Let's take care of the 0 exponents first. Anything other than 0 to the 0 power is just 1. So this whole thing is just 1. Now, we have a mess of negative exponents happening. We have some inside parentheses and some outside. Let's just deal with the inside parentheses first. We have this y to the -2 and the x to the -2. That 3, however, that does not have a negative exponent. So I am just going to move the x and the y to the denominator, keep the 3 in the numerator. And all of that is being raised to the -1 power. Raising something to the -1 power is taking the reciprocal of it. So everything gets raised to the -1 power, which means everything moves from its current location. The 3 on top will move to the bottom. the x squared, y squared will move to the top. And we're in simplest form. So we can put a circle around it, or whatever shape that is. With the 2's there, it kind of look like eyes, and then a weird nose, and then like the chin is sideways, and it's like a potato. But I keep going on. Number 39, rewrite the expression using positive exponents. There's not a lot to do here. We have 5, and then we have capital A and capital B, which they decided to use those for exponents, which is fine. The B is to the negative exponent, so I will move that to the denominator of the fraction. The 5 and the A will stay up top, and it will just become B squared once it's moved. And honestly, that's where I stop. There isn't a lot of work to show here because that's the best I could do. And let's move over. Whoa. Rewrite the expression using positive exponents. Oh, look, we have a 0 exponent though. I love 0 exponents. So the negative 3 to the 0 power, that just becomes 1. Now we can deal with this negative exponent, x to the negative 3. That will move up top. It becomes x to the 3rd over 4. I can circle that. Okay, let's add some polynomials. Remember, they have to be like terms, so they have to have the same variable to the same exponent. So all my variables in 41 are c, which is great, but 3c to the 6 can only go with other c to the 6's. And when you add them together, you're really adding their coefficients. So 3c to the 6 plus 6c to the 6 is 9c to the 6th, which we can already go through and eliminate 2 of these answers if we wanted to. Okay, and then, we have some c squareds. Oh, went too far. There, right there. So 6c squared plus negative 3c squared is plus 3c squared. We subtract their coefficients. The variables and the exponents do not change at all. And the last thing, we have negative 6 plus 7. So negative 6 plus 7 is plus 1. So which answer is this? D. All right, and 42, find the difference. Okay, so we are going to turn this into an addition problem, just like we have above. Let me zoom out a little bit. Okay, and I am going to do that by changing this to a plus sign, but I can't just change it to a plus sign. I now have to change the sign of everything after it. So the negative 7z to the 6 becomes a plus, the negative 9z to the 3rd becomes a plus, and the minus 3 becomes a plus. Now that whole right side is all positive numbers. And I'm going to combine my z to the 6th first. So negative 2 plus 7 is 5. And it's positive because the whole thing is positive. Now, I actually could find the answer right now because there's only one with a positive 5z to the 6th. But let's keep going. Let's pretend it's not that easy of an answer. So negative 2z to the 3rd will combine with 9z to the 3rd. They're like terms. So 9 minus 2 is 7. And finally, we have a negative 7 and a positive 3. Well, the negative is going to win in this case. Negative 7 is bigger than the 3, so our answer will be negative. It'll be negative 4. But you knew that because the other two numbers said it had to be B. Oh, 43. We have another one to subtract here. Okay, so I'll make that a plus, change that to a plus. Oh, and then the next two become minuses. So now when we're combining, it's 3x to the 3rd plus negative x to the 3rd, which is just subtracting. So 3x to the 3rd minus x to the 3rd is 2x cubed. We have 9x squared and 4x squared. Both are positive, so we will add them, plus 13x squared. And in this last one, we have a minus 6. I will just write that on the end. Cool. And the last one on this page, we have to find the product. It's two binomials though. So we have to take each term in the first one, each of those, and multiply by the entire second thing. So I'm going to make it a plus negative because it will make the distribution easier. And I will take the x from that and multiply it by x minus 2, and then the plus negative 3 times x minus 2. If you didn't make that a plus negative, a lot of times people don't remember to distribute a negative sign to both of the second terms. But here we go. X times x is x squared. X times negative 2 is minus 2x. Plus negative 3 times x is negative 3x. And negative 3 times negative 2 is positive 6. And our middle terms are negative 2x plus negative 3x. That's x squared minus 5x plus 6. And that answer is B. Now we're multiplying another binomial. So I will take 4x plus 1 and multiply 4x times 4x minus 3 plus 1 times 4x minus 3. And do the distribution there. So that will be 16x squared. Don't forget to multiply the x times x. 4x times negative 3 is negative 12x. 1 times 4 is 4x. And 1 times negative 3 is negative 3. And usually if this is done correctly and everything's in standard form, those two middle terms will often be like terms, so we can subtract those. 16x squared. Now, negative 12 plus 4 is negative 8x minus 3. Oh, they like every permutation of this. But that one is the correct one. Okay, x plus 4 and x plus 7. X times x plus 7. Don't forget everything in the first one gets multiplied by the entire second one. So we have x squared plus 7x plus 4x plus 27. Oh, 28, not 27. Get out of there. 28. Okay, there's a middle term here, 7x and 4x. You can add those together. That's x squared plus 11x plus 28. And that is C. Great. Oh, let's just keep going. Oh, here we have a binomial times a trinomial. All right, this is the real reason why I do my distribution the way I do, and I don't use FOIL. Not that there's anything wrong with FOIL, but it honestly doesn't work for question number 47. But my way does. Everything in the first one times the entire second term. Plus 5 times the entire second term. Ooh, I'm like sneaking over in the other column. And those have radicals. Okay, distribute. Now we're distributing to 3 terms. So this will be x to the third minus 2x squared plus 3x plus 5x squared minus 10x plus 3 times 5 is 15. Now we have two sets of like terms here. We have this one, negative 2x squared and plus 5x squared. And we have this one, 3x and negative 10x. So the x to the third doesn't have a like term. Negative 2x squared plus 5x is plus 3x squared. 3x minus 10x is negative 7x. And the 15 doesn't have a like term. And my answer is A. Oh, now we're into radicals. Awesome. So there's a lot of different ways to solve these. The fastest way to simplify this 300 would be to break it up into perfect squares. So the biggest perfect square I can think of that goes into that is the square root of 100 times the square root of 3. And the square root of 100 exists. It's 10. 10 times the square root of 3. That would make my answer B. However, if you don't want to do it that way, you can do it with a factor tree, I think they're called. Just list the number and just keep dividing small prime numbers into it as much as you can. So you could do 2 first, and that would be 150. 2 times 150. And 150, 2 again. Sure, let's just keep going with 2s. That's 75. Oh, 2 doesn't go into 75, but 3 does, 25 times. And that's 5 times 5. And then you can write all of these factors under a square root symbol, square root of 2 times 2 times 3 times 5 times 5. And because this is a square root, we're looking for doubles. So we have double 2s. We can move 1 on the outside. Double 5s. 5 times 5 is 25. The square root of that, move a 5 on the outside. And we can rewrite our answer. 2 times 5 times the square root of 3. 2 times 5 is 10. 10 times the square root of 3. Now, if you've not seen either of these methods so far, you'd be like, why would you ever do that second way? It takes so much more time. In order to do the first one, you have to, first of all, know what all the perfect squares are. And second, be able to divide them out very carefully. The other way, you can do not only square roots, but cube roots or fourth roots or fifth roots or anything. You just, if you're doing a third root, you're looking for triples of a number instead of doubles. All right, let's move on. Let's go up to 49. All right, square root of 20, that's an easier number. Here, I'll do this the factor tree method. 2 times 10, and that's 2 times 5. So it's like the square root of 2 times 2 times 5. And 2 times 2, you can move one of those out. Our answer becomes 2 times the square root of 5. The faster way, 4 goes into 20. It's 4 times 5. And the square root of 4 is 2. 2 times the square root of 5. All right, 48. Let's do factor tree. All right, 2, 24. 2 and 12. 2 and 6. 6 is 2 and 3. Ooh. This one's nice. So the square root of 48 is the same as the square root of 2 times 2 times 2 times 2 times 3. 2 times 2, pull it out. 2 times 2, pull it out. And then the 3 is left. So 2 times 2 times the square root of 3. It's 4 times the square root of 3. Or it's just 16 times 3. And the square root of 16 is 4. 4 times the square root of 3. Okay. Yeah, let's write it nice and big because we're proud of our answer. 4 times the square root of 3. Okay, now if you multiply radicals, you multiply the radicands, the part under the radical, by each other, and you multiply any of the coefficients by each other. But there are no coefficients in square root of 30 times square root of 12. So instead, I will just multiply the radicands. So 30 times 12 is the square root of 360. Oh, that's lucky. Okay, you know what? Because it will probably be fun. Let's do the factor tree method. This will go on for a while. Now, you might want to be like, oh, let's do 36. Let's do 10, something. No, just keep it all prime numbers. It's actually easier if you do it that way. So 360 divided by 2 is 180. And 180 divided by 2 is 90. 90 divided by 2 is 45. Okay, we can't use 2's anymore. Well, at least not very next. I'll use a 5. And that goes to 9. And 9 is 3 times 3. Okay, so to rewrite this, it will be 2 times 2 times 2 times 3 times 3 times 5. And we're looking for doubles, and they're all not doubles. Like, we have double 2's. Great. But then we have a leftover 2. That's fine. It stays underneath. It becomes the part of the new radicand. 3 times 3, that's a double. That moves out. But that 5 stays underneath because it has no other, there's no other 5. So the 2 and the 5 stay, and we'll multiply those by each other. And we'll get 2 times 5 is 10. And we moved out a 2, and we moved out a 3. 2 times 3 is 6. Becomes 6 times the square root of 10, which is C. Imagine that. All right, almost there. You almost made it. 2 times 60. Huh. 2 times 60, huh? Well, 2 times 6 is 12, so that's square root of 120. Once again, let's do this the fun way. And that's 60. And 2 goes into 60, and that is 30. And 2 goes into 30, and that's 15. And 3 goes into 15, and that's 5. So 2 times 2 times 2 times 3 times 5. Okay, I can get behind that. So it's the square root of 2 times 2 times 2 times 3 times 5. And there's not a lot you can actually pull out of this one. The 2 times 2, that's it. The 2, the 3, and the 5 all have to stay. I'm going to multiply them back together. So this will be 2 times the square root of 2 times 3 is 6. 6 times 5 is 30. 2 times the square root of 30. The square root of 30 looks like you can continue to simplify it, but you cannot. Okay, now we're adding radicals. Oof. Now, in order to add radicals, they have to be identical radicals, and these clearly are not identical radicals. So first, we need to simplify them, and then we can add them. So 54, here we go, 2 goes into 54, 27. 27 is 3 times 9, which is 3 times 3. Okay, so square root of 54 simplifies to 3 times the square root of 6. Hopefully you could follow that. Then 96, let's see, 96 divided by 2 is 48. And we're back onto 48. That's 2 and 24, 2 and 12, 2 and 6, 2 and 3. Oh, that's not even a 2. Okay, how many pairs of 2s do we have? 1, 2. So 2 pairs of 2s, and then 2 times 3 is 6. So that will be 4. Well, let me change back to the other color. That will be 4 times the square root of 6. Okay, the good news, our radical part is identical, so we can add these together. So what we were really adding is the coefficients, just like with exponents. 3 plus 4 equals 7. 7 times the square root of 6. That's C. Boy, did I get excited putting these these radical questions on. Okay, 6 times the square root of 2 plus 3 times the square root of 2 minus 2 times the square root of 2. Hey, good news. They're all the same. They're all like terms. So we can just add and subtract their coefficients. 6 plus 3 is 9. 9 minus 2 is 7. This is 7 times the square root of 2. All right, this one, not so much. But only one of them can be simplified, and that's 3 times the square root of 12. The square root of 12 is 2 times the square root of 3. So it's 3 times 2 times the square root of 3, and 3 times 2. That's 6 times the square root of 3. So I'm going to replace minus 3 times the square root of 12 with minus 6 times the square root of 3. And that's not a good place to do that. So let's do it over here. 2 times the square root of 3 minus 2 times the square root of 4. Wait, 2 times the square root of 4, that's 2. That's minus 2 times 2. Minus 6 times the square root of 3. Okay, so 2 times the square root of 3 minus 6 times the square root of 3 is negative 4 times the square root of 3 minus 4, and that 2 times 2 is the 4. And you can't go any further. Those aren't like terms. You can't combine them any further. It would be nice if we could, but we can't. So we're just going to leave it like that. And if you wrote it with negative 4 minus 4 times the square root of 3, that's also right. Those are both right. Great. Nice job, everyone. Oh, simplify the whole radical expression. So we are going to take the square root of 49 and the square root of a to the 8th. Okay, the square root of 49 is 7. That's cool. The square root of a to the 8th. Square root of a to the 8th. Well, there's 8 a's being multiplied in here. Okay, so square rooting them, you get a to the 4th. It's kind of like dividing 8 by 2. A to the 4th. Hopefully that's one of our answers. Yay, it's C. Okay, the next one. These are being multiplied. We don't need like terms. Multiply the numbers on the outside. 2 times 3. That's 6. Multiply the numbers on the inside. 10 times 12. That's 120. And we already did the square root of 120. It is 2 times the square root of 30. So this is 6 times 2 times the square root of 30. And 6 times 2 is 12. Now you can do this because the square root of 120 is kind of a constant value. And if we figured it out to be 2 times the square root of 30 before, it is always going to be 2 times the square root of 30. So you could just copy it later, and that's C. It's always good when the answer you get is actually available. And I believe this is finally our last question. Okay, so multiply the numbers in front. 2 times 1, which is just 2. And then multiply the radicands. So 14 times 4, which is 56. And then q times q is q squared. Don't sleep on the q times q being q squared. Now, if we take the square root of this, the square root of 56, I just realized I could have done this way faster. 2 times the square root of 56 is 2 times the square root of 14. And the square root of q squared is just q. So we have a lot of numbers that aren't underneath the radicals. We have a 2 times 2, which is 4, and that times q is 4q times the square root of 14, which is great because that's b. Other thing that could have been faster, and this one, 4 does have a square root, it's 2. And then the square root of 14 would have just stayed. I could have taken the square root first, but that's okay. 4q times the square root of 14 is number 58. And we are done. Hopefully you made it all the way through this. And good luck on your test.